the things that we were doing were building up into this topic, linear programming. Essentially, when you deal with linear programming, you're talking about taking equations, right? And depending on your situation, you're going to develop an inequality relating to it and represent all of that on a graph. And when you represent all of that on a graph, you're going to be able to find some solution set, some group of values that will help you with either maximizing or minimizing your problem, whatever your problem may be. So in the instance we're dealing with linear programming problems, majority of the things that it will surround will be maximization, and most times you'll see a profit maximization. So if you look through past papers and you look at questions involving linear programming, you're going to find questions where they ask you to determine the maximum profit and whatnot. So we'll get into all that in a little bit, but this is essentially what you're going to be creating. You're going to be creating a graph of inequalities, not just one inequality, but multiple. And where all these graphs intersect, that's where your solution set resides. So if you'll recall, Form 3 would have done simultaneous equations. And back then, when you did simultaneous equations, if you solved it graphically, you would find one common point where the two lines would intersect, right? When we deal with inequalities now, we're not dealing with just one point. We're actually dealing with a set of points, a collection of points, because an inequality, a simple inequality, for example, like y greater than or equal to 1, that solution set would be the value 1, but also every single value that is greater than 1. So when we deal with linear programming types of problems, you're dealing with inequalities, you're dealing with graphing those inequalities, you're dealing with finding the set of points that will make up this solution. All right, so how do we get from a worded problem into a graph to even try to get values? So the first thing we have to do, if you all can recall some of those skills from, let's say, Form 2 and Form 3, where you would be given a statement and you have to translate it into algebra, this is where that skill is going to come in, because most times your linear programming problems would come in a worded problem form, right? And they'll give you a scenario and they'll tell you, well, come up with the inequalities, then graph these inequalities, then find the solution. So this is where we're going to get started with the linear programming, right? The first task that we will have to do is create a collection of constraints. So when I say a collection of constraints, I'm talking about a set of inequalities based on the situation, right? So here my problem states that a student has $265. She wants to buy X jerseys at $25, Y shirts at $35 each. She must buy at least 2 jerseys, but no more than 5, and she must also buy more than 1 shirt. So in that statement, right, if we break it down sentence by sentence, we realize that there's information inside there that we can create constraints based on. All right, so let's start off first of all by identifying what is this unknown that we're working with, because our constraints are going to be focused on some sort of unknown. They're going to be focused on 2 particular variables that we want to get the solutions to. All right, so in this problem, notice the second line, the second statement, which says she wants to buy X jerseys at $25 each and Y shirts at $35 each. So right here, you get the 2 variables, you get your 2 unknowns. The number of jerseys that she's going to buy and the number of shirts that she's going to buy. All right, so right there, we already have our variables, X and Y. I forgot to change the color, oh yeah, yellow. All right, nice. Makes my life easier. All right, so yes, X and Y. All right, these are our variables. So if I want to establish constraints based on the statements that I'm given here, I have to make them based on X and Y. So every single inequality that I develop is going to either involve X, Y, or both X and Y. So read back the statement, and I want everybody to see if there's any particular part of these statements here that you could create an inequality for. You take your time, right? I'll give you all some 3 minutes, right? Inside here you have 3 constraints, I believe. So see if you all can develop at least one constraint, and we'll continue our discussion after that, right? So 3 minutes, think about it in terms of X and Y, based on the information they gave you here. What inequalities can you develop? Okay. All right. So let's see. She must also buy more than one shoot. So if you're saying Y is greater, I hope I'm not blinding anybody, Y is greater than equal to 1, then you're correct. Because in this particular statement, the shoots, the number of shoots is represented by the variable Y. And the number of shoots that she must buy, right? So they say she must also buy more than one shoot. So you're doing this one, right? Y is greater than or equal to 1. Well, technically, we would do greater. It should have been a greater than, because they just said more than. But I think when I was doing the graph, I did it greater than equal to 1 because I needed solutions. And on this case, if I use Y is just greater than 1, because it's strict, I would not be able to use any values on that line. But she must also buy more than one shade. That's correct. That's one of your constraints. So that's good work there. That's the first one. Anybody else wants to tell me a constraint that they were able to identify? So what inequality were you able to develop? Alright, so we have X is less than or equal to 5. Nice. That's a start. Alright, because we do have, she must buy at least 2 jerseys, but no more. And this no more, that's a good one. No more than 5 jerseys. So X must be less than or equal to the 5. So there you go. That's a piece of it. Who wants to help complete the other piece of it? There you go. 2 is the lower limit here, because this one we're going to get a compound inequality. The reason we're getting a compound inequality, they're saying that the constraint for X, yes, you have to buy at least 2 jerseys, but you can't buy anything more than 5. So that's how we're going to get a compound inequality here, whether we decided to write it as 2 separate inequalities, where you would have X is less than or equal to 5 and X is greater than or equal to 2. We have a compound inequality, alright? And once we have this constraint properly set between 2 and 5, we're good to go, because that is the complete constraint for X. So there's another one. Can anybody tell me what they think the other one going to be? This final inequality that you have to find inside here is just a slight bit. Okay, so now that we're step back in finally. Like I was saying, the compound inequality for X is simply because we're restricting the value of X between 2 and 5, as that's what they said. You have to buy at least 2, but you can't buy more than 5. So that's why we do a compound inequality here. Now for the final inequality, like I was saying, it's a slight bit of a challenge, but pay attention to the information that they give you, and you'll be able to come up with the constraint. So let's see. Think about it. So student has $265. She wants to buy X jerseys at $25 each and Y shirts at $35 each. So we've already developed a constraint for buying at least 2 jerseys but no more than 5. And we've also established an inequality for buying more than one shoe. So can anybody figure out the final inequality? So you don't need to have the complete inequality, but you can tell me what information you think you're going to use to come up with the final inequality. Alright, so let's write that down. She says 265. This is more than or equal to. Alright. Okay. You're not too terribly off. You don't have the full set of information for the inequality, but yes, it has something to do with this 25. Yes, it has something to do with this symbol. Alright, so you're on track. So think about it like this. I have a question. What you gonna spend the $265 on? Why is more than or equal to 25? Nah. Why can't be more than or equal to 25? Why has to be more than or equal to 1? But the 25 is the price for a jersey. So think about it. Anybody can answer that question for me. If you can answer that question, you'll be able to figure out how to connect the 265 to the X and the Y. So what am I spending the $265 on? Apples, grapes, dogs, chocolate. There you go. Jerseys and shirts. So if you have $265, you want to spend that $265 wisely on jerseys and shirts. Right? And you want to at least maximize how you spend that money. So we know we have to buy jerseys and shirts. So I have a question. What would X plus Y tell me? That's the number of, alright, so yeah, that would be the number of jerseys and the number of shirts added together. So that's the total number of jerseys and shirts I could buy. Alright. What about this? What would 25 times X tell me? So think about this a little bit now. Think about it in terms of buying stuff. $25 is the cost of the jerseys. X is the number of jerseys. What does 25X say to us? Lovely. That's it. That's the amount of money you spend on jerseys. So if 25X tells you how much money you spend on jerseys, how will we figure out how much money we spend on shirts? Lovely. 35 times Y. And then I know I'm not just buying jerseys only, and I'm not just buying shirts only. So if I want to figure out how much money I spend in total buying jerseys and shirts, what do I do? There you go. You add the two. Now, this tells me how much money I spend in total on jerseys and on shirts, right? 25X plus 35Y is how much money I spend in total buying jerseys and shirts. Is there a restriction on how much money I can spend? Lovely. We only have $265. So if we only have $265, how would we write an inequality now to represent the total amount of money spent on the jerseys and shirts, but ensuring that it does not exceed the 265? That's it. That's all there is to it. So that's what we do with linear programming. We take our conditions, our limitations, and we model them as inequalities. So that way, we don't just go doing a problem like this, just guessing values. There's a reason behind everything we do. So from what you all have done, which is very, very good, we have 3 constraints. And we can use those 3 constraints to help us with being able to get a graph and whatnot. Alright? So write down the 3 inequalities, like I was saying. This is this one, this one, this one. Alright? 3 inequalities. Once you have those done, we're going to continue with the problem. All right. So like I said, these three inequalities, these are your conditions, these are your constraints. These tell us the restrictions involved in the situation. All right. Now, like I was mentioning earlier, we did linear equations back in Form 3. We know about solving simultaneous equations. We know with simultaneous equations, there's one solution for the two equations. But here, notice something, we have three inequalities. All right, and we have two variables. We also, in dealing with inequalities, know that the solution is not just going to be one single value, right? We can have multiple possible solutions. But in the case of a maximization problem, as in this one, you're going to learn that one point in particular is going to be the most significant one for us. So ultimately, this one is going to be a maximization problem because the person is going to be selling back the items they purchased to make a profit.